Okay, students, let me start the class. In the morning's class, I was discussing this particular curve, and that is when the time was up. So I am going to repeat it once again, little bit. You can see this particular curve, which is present in almost all textbooks. So I was telling that whatever curve I have written early upper side, it is not written in any textbook. Such curve or even this particular curve. These are not present in any textbook. I have written it purposefully so that students can easily understand these concepts. But this particular curve is present in almost all textbooks. It is called as output characteristics. Here x-axis is VCE, which is an independent factor, and y-axis is IC, which is dependent on VCE. So they plot a curve of VCE versus IC, and when VCE increases in the beginning, gradually IC also increases. After some time, when VCE reaches a particular value, IC remains constant there. So this is the particular characteristics which they have found in even BJT and even in MOSFET. The curves are similar to these two active devices. We can arrive at some facts looking at these curves, that at a particular current which is below certain threshold, we can say that the transistor is completely off. So that is this region A. And at a region B, where for a given VCE, IC remains almost constant. In other words, the transistor works like a current source after a particular value of VCE is maintained. In the morning class, I have already told you that when the switch is completely on, there will be a zero voltage drop across it. So that is region C, where you can see voltage drop across the transistor is lesser, and then there is a particular current also flowing there. That is region C. In region B, you can see VCE is larger than 0, much larger than 0, which means the transistor is not fully on, neither it is fully off, because there is a current which is maintained. So this region is called as active region. In this active region, transistor is highly sensitive. That is why it is called as active region. And in the region C, it is called as saturation region, because the voltage drop across the switch is lesser, means it is turned on, and there is collector current also. Whereas in region A also, there may not be any voltage drop across the switch. Still, current is not there, so it is cut-off region. Now, this region D is called as a breakdown region. Oh, just a minute, I will share the screen. Just a minute, I forgot to share the screen. No, I have shared the screen. I have shared the screen right now. Is it not visible to anyone there? Screen is not visible to anyone? Anyway, recording is on. So even if there are some issues, later on you can go through the video. Fine, let me proceed. This region D is a breakdown region, wherein if VC is much larger across the device may not withstand the voltage across those two junctions, and the transistor will simply burn out, or it will simply break down, where the current will suddenly increase and the transistor will become a short circuit there. That is called breakdown region, which is a dangerous region, beyond which the switch will not work at all, or the device will not work at all. So there is a tabular column, you can just refer to this. In the cutoff region, for a common emitter configuration, output voltage is VCC, saturation region it is 0, active region it is VCC by 2, as I had already told earlier. whereas output current is 0. Is completely on, it is connected to ground, so the complete voltage is across the resistor RC. So current is VCC by RC. In the active region, as there is a half of the voltage across the transistor, half of the voltage across the resistor, it will be VCC by 2RC. So which means that at the midpoint of the curve or in the exact half way, the current is half. Current is maximum at saturation region. So sometimes we call this VCC by RC as IC sat, collector current saturation. That itself is the maximum current which can flow through the device because switch is completely on. Now in the cutoff region, base to emitter junction is reverse biased and base to collector junction is also reverse biased. In the sense, the PN diode from base to emitter, it does not have enough drive, it is reverse biased. And even the base to collector junction is reverse biased because the transistor is not on. In the saturation region, base to emitter junction is forward biased. If you visualize that PN is forward biased because there is a 0.7 volts. Similarly, in saturation region, base to collector junction is forward biased. Base to collector is again that P and N. That N is connected, but in the saturation region, across the switch as the voltage is 0, base is at a higher potential than the collector. Which means collector to emitter, the drop across the device is 0, whereas base to emitter, there is a PN junction, and base to collector also there is a PN junction. Base is maintained at 0.7 volts, whereas collector is maintained at 0 volts because of the switching action. So naturally, that base to collector junction is forward biased. But in the active region, base to emitter junction is forward biased. The base to emitter diode is working. Base to collector junction is reverse biased. Why? The collector is at a higher potential than the base. Collector is N, base is P. Collector is at VCC by 2, whereas base is at 0.7. So naturally, N region is at a larger potential than the P region. So base to collector junction is reverse biased. You can remember this. Whenever we want the switch to be in active region, we should forward bias the base to emitter junction and we should reverse bias the base to collector junction. That means we should ensure that the transistor is not fully on. If at all we want to use it as a digital circuitry, then we should either give a positive pulse at the base so that it will turn on, so both junctions are forward biased. In the cutoff region, both junctions are reverse biased. So there is a reverse bias, forward bias, reverse bias, forward bias, forward bias. 3 combinations are there. One more, reverse bias, forward bias condition will never occur. If the base to emitter junction is reverse biased, base to collector junction can never be forward biased. And even if it is forward biased, there is no use as such for the device. So the 4th combination does not exist as such. So let me proceed now. Some notes here. For biasing the BJT, the resistors are utilized with the proper values by using KVL. And the basic common emitter circuit can be written like this. In general, what we do is, whatever circuit I told, that does not exist. Whatever circuit is I am showing now, this exists. And what we do is, we don't have a power supply exclusively for the base. In the beginning, I showed you a circuit, separate VBB, separate VCC. But why should we have a separate VBB when we can work only with a single power supply? So what we do is, single power supply is connected to collector also, base also through these resistors. And we can easily calculate the value of RB, value of RC using this circuitry. And anyhow, output we are taking at the collector, emitter we are grounding. To the input, we can give AC voltage directly. This AC voltage will be always in millivolts and microvolts. So we can give this to the input directly. Now this will be the actual circuit which we will be using initially. So with respect to this circuitry, we can say that apply KVL to the input. See, you can apply a KVL in this manner. VCC to RB to VB to ground. Apply KVL in this way. We will not have any dual power supplies. We will have only single power supply from now on. So, complete VCC is between RB and VBE. So, naturally, VCC minus VBE divided by RB is the base current. Similarly, collector current is VCC minus VCE divided by RC. Now, as we are connecting DC here to the base for only biasing purpose, we will be giving only some amount of base current to the base such that transistor will be half on. If the transistor is half on, when we apply the AC input, this AC input should not have DC component. If the AC input, any signal which is having a DC component, that DC will induce base current into the PN junction, driving the transistor into saturation. That should not happen. We choose this value RB in such a way that a transistor is only half on. So, this AC should not turn the transistor completely on or completely off, as I told you in the morning's class about the clipping issues or the unfaithful amplification. So, for faithful amplification, DC is supplied only through the battery and only pure AC should be supplied. So, if at all any signal which is input to the amplifier is containing part of DC, that DC should not be given to the amplifier. So, the solution is what? We can connect a capacitor here in series. Later we will be seeing that circuit. When we connect a capacitor, capacitor passes only AC, it blocks DC. You already know the formula for the reactance of the capacitor, X is 1 over 2 pi Fc. So, for DC, frequency is 0. Frequency 0 means 1 over 0 is infinity, that is the reactance of the capacitor. So, when we connect a capacitance here, it will pass only AC. That is why coupling capacitors can be utilized to block DC, then the circuit can be rewritten in the improved fashion. Now, look at this particular circuitry. From now on, we will be writing the circuit diagram in this style, which means we will not be exclusively showing any battery anywhere, because why to keep on writing the battery symbol and why to keep on writing plus and minus? Instead, we simply put one bubble there, we simply write plus VCC. And then anyhow we have RC, anyhow emitter is connected to ground. And again from VCC to base you have RB. At the input we will have a capacitor, at the output also we will have a capacitor. Why? The power supply is DC should not go to the output. Output required is also AC only. Input required is also AC only. For example, I am speaking to the microphone now. I speak to the microphone, my voice gets converted into electrical signal, that is AC signal. Because my vocal cord is moving up and down. When my vocal cord is moving up and down, naturally in the microphone, the diaphragm will be moving to and fro. When the diaphragm is moving to and fro, it is going to produce AC signal. That AC signal is going into the laptop now. In the laptop, it is going to be amplified. After it is going to be amplified, in the laptop there is one ADC, analog to digital converter. That ADC will convert my voice into digital, and digital signal is going to be connected to the microprocessor in the laptop. And the microprocessor is going to process the signal in the digital signal processing, and it is going to modulate this as an analog carrier. It is a 2.4 gigahertz carrier wave in the Wi-Fi connection. So, through this 2.4 gigahertz radio wave, through the Wi-Fi, it is reaching you. This is what is happening between you and me. So, in the microphone, it is AC. Even in the outside atmosphere, radio wave is also AC. Nature is basically AC. When the bird is singing, bird's vocal cord is moving to and fro or up and down. It is basically AC. When you touch the string of a guitar or a veena, when you pull the string and again you release the string is going to move to and fro for some time. When it is moving to and fro, it is producing a sound, which is basically AC. AC does not mean always alternating current. AC always means there will be a wave which is going to both sides, upside and downside or left side and right side, in whatever way. So, all natural signals are basically AC, because whether it is sound, Any sound is basically a vibration of some objects, whether it is a string or whether it is a leather. In case of tabla, mridanga, it is a leather, or in drums or flute, it is a resonance which is happening within a cavity. Inside a flute, when they blow air, air column is going to vibrate within that particular space within the bamboo flute. So that is how sound is produced. So basically sound is AC. Now we need an amplifier which can amplify my signal to a larger volume. Look at this particular circuitry. At Vin, my microphone is there. Think that way. This particular amplifier circuit is already there inside my laptop now. At Vin, when I speak, my speech will be hardly around a few millivolts. If I speak still lesser volume, it may be microvolts also. Hardly around few millivolts, because when my vocal cord is vibrating, voice is being produced. Generally, gents will have a voice frequency of around 300 to 600 hertz. Ladies will have a voice frequency of around 600 to 900 hertz. And children will have a voice frequency of much larger than 900 hertz, maybe 900 to 1200 hertz. In general, we can say that human voice frequency is between 300 to 3400 hertz, and they take it as a 4 kilohertz bandwidth there, which means when the vocal cord is vibrating, minimum 300 times, maximum maybe up to 1200 times or more, it is going to vibrate. Even when a bird is singing, its vocal cord is vibrating. Even when music is being played, the instruments, some parts of these instruments like a string or a leather are going to be vibrating. That is how sound is produced. So when I am speaking here, let us say microphone is connected at Vin. Now the microphones, if at all it is connected to another transistor internally, microphone will have another MOSFET internally. So that DC should not come here. That is why there is a capacitor here. And then we have the regular amplifier circuit. You have to always visualize one more battery supply here. We don't exclusively write it from now on, because we are all engineers. We use more of symbols. All these symbols only engineers will understand. This is a ground symbol which electrical and electronic engineers will understand, or all other engineers will understand. This is a transistor symbol which electronic and electrical engineers, all other engineers will understand. Here it means that transistor physically is not like this. Transistor is physically silicon. But for our own convenience, we write symbols, and symbols give the complete meaning of the device. Just look at this: base, collector, emitter, arrow mark here. Arrow mark means current is going from collector to emitter. And base to collector, there is a junction here. Base to emitter also, there is a junction here. This line is indicating that. So the symbol indicates the working principle of the transistor. Similarly, capacitor, you can see this capacitor. If DC current comes, it cannot go to the other side. If AC current comes, because of the electrostatic induction, AC is connected to the other side. Similarly, look at the resistor symbol. Resistor symbol simply means that when current comes here, it is to go up, down, it go up, it will come down, it will go up, it will come down, and current will become tired. That is how you have to visualize. They make symbols in such a way that the character of the device is indicated there. Otherwise, physically, these symbols are not like that. Sorry, physically, these devices are not like that. They are only symbolic. So, we need not write battery symbol again and again. These are all symbolic. So, this way, AC signal comes here. Now, we have set a transistor to a Q point of VCC by 2. We apply a small signal at the base. Gradually, the small signal at the base will cause the transistor to switch up and down, and it will create a large signal at the output with a 180-degree phase shift, as I told you in the morning. So, a few millivolts of change in the input is going to cause a few volts of change at the output, depending upon the value of VCC. Now, this particular change, it is already containing the DC value also. The DC should not come out, because output can be a speaker, or it can be connected to an ADC. It can be connected to any other respective device. So, here the DC value which is used for biasing the transistor should not be connected to the output. That is why we have one more capacitor. That is the purpose we use these two capacitors. Here the capacitor connected to the base is generally given a symbol CB, meaning it is a blocking capacitor. And the capacitor connected to the collector is generally given a symbol CC, meaning it is a coupling capacitor. These meanings have a different context. For example, this is specifically blocking capacitor, this is specifically coupling capacitor. Why they are called so? In amplifier, inside the electronic systems, it is not actually only one amplifier. There are multiple stages of amplifiers. There is something called pre-amplifier, there is something called middle stage amplifier, there is something called power amplifier and output. For example, let us say from a satellite, a signal is being received at the dish antenna. Satellite, let us say if it is a geostationary satellite, it is 36,000 kilometers away from Earth. So when the satellite is beaming its radio waves onto the surface of the Earth, the signal will not be in millivolts. It will be in microvolts. Sometimes it may be in nanovolts. Sometimes it may be in picovolts. I'll give you one more example. Space stations are being launched and spaceships are being launched. There are spaceships which have already crossed the solar system. They keep sending signal all the way. Imagine we are on Earth. Apart from that, there is Jupiter, Saturn, Uranus, Neptune, Pluto. Solar system ends there. Let us say a spaceship is moving away from Earth. The signal deteriorates when the distance is increasing. So, such a minute signal is received on Earth, which means the signal need not be in picovolts also. It may be in femtovolt, attovolt, zeptovolt, yoctovolt. It may be 10 power minus 15, 10 power minus 18, 10 power minus 21, 10 power minus 24. Such small signals can be transmitted, such small signals can be sensed also. So in such case, if there are such small signals which are going to be sensed, what we are supposed to do? What we are supposed to do is, we will pick up such minute signals and we will connect them not just to one stage of an amplifier, we will have multi-stages of amplifiers. Because one stage of an amplifier may give hardly 60 times, 100 times gain. That is not enough for us because our signal is in 10 power minus 12 or 10 power minus 15. In such a case, we need more stages of amplifiers where a picovolt or a femtovolt is amplified to millivolt or volt. That is when we connect one amplifier to another amplifier to another. That way, 3-stage, 4-stage, it is called multi-stage amplification. For that reason only, this is called as coupling capacitor. Meaning, one stage's output is coupled to the next stage. So, to the next stage, this itself can be a blocking capacitor. DC is being blocked and AC is being coupled. So, that way, either blocking capacitor or coupling capacitor, purpose is the same. Only the terminology used will be different based on the context. Otherwise, they are the same capacitors. Sometimes they may be having the same values as well. So, dear students, remember this particular circuitry. From now on, we will be using this style of circuit diagram only. The breakdown region should never be used as the BJT gets damaged due to high value of the collector current. This I have discussed already. There are some notes. The active region is sometimes called as linear region as the output is proportional to the input. But as the output current is constant, the BJT can be utilized as a constant current source in the active region. This linear region terminology is utilized only in case of BJT. With MOSFET, the meaning of linear region is something different that we will see later on. So, this basic common emitter circuit discussed so far is called as base bias or fixed bias circuit, in which there are only two resistors for biasing. Only two, one at the base, one at the collector, which is our minimum requirement. When biased for the Q point or quiescent point, the base to emitter junction is operating in a nonlinear fashion. when the input signal is applied. Thus, it is very difficult to accurately depict the behavior of the device. However, for all practical applications, the device can have an approximate equivalent circuit as follows. Look at this, we can have an equivalent circuit. Means there is a base to emitter junction, which is a diode. There is a collector to emitter connection where we have a current source. You already know that in the active region, current is remaining constant. So that can be written as a current source. And this current IC is nothing but beta into IB. So we can simply model this transistor symbol with one diode symbol and with one beta IB. This type of model, it started from Eber's mole model. It was one of the fundamental models which the scientists developed for analyzing the transistor circuitry. Later on, we are going to have an analysis of the transistor circuitry. There, such model is going to be helpful for us. We will be seeing those models later on. Let us see an exercise. For the base bias, VCC is 12 volts, beta is 80, RB is 470 kilo ohms, RC is 1 kilo ohms. Find out the power dissipation of the device and comment on the region of operation. I will give you around 3 minutes time. Can you try it out now itself? It's a very simple calculation. You already know that KVL IB is VCC minus VBE divided by RB, and that way you can easily find out IB. IB into beta, beta is given, you can find out IC, and when you find out IC, VCE you can find out by VCC minus ICRC itself is VCE. Just visualize the circuitry and note down these values. VCC 12 volts, beta equals 80, RB equals 470 kilo ohms, RC equals 1 kilo ohms. Note down these values. I will give you some 2 to 3 minutes time. Those who work out, put the answer in the chat box. Later on, I will confirm whether the answer is correct or wrong. Until then, just look at this, and this is the circuitry. This is the circuitry. RB, RC, and beta is given. VCC is given. This is the circuitry. Apply that formula and immediately tell me the answer. I'll keep looking at the chat box for the next 2 minutes. Yes, VB is always 0.7 because we will be taking only silicon as an example. Okay, 23.07 milliwatt. Lokesh Biswas has given the answer. Let us verify. IB is VCC minus VB divided by RB. 12 volts minus 0.7 divided by 470K. So 12 minus 0.7 divided by 470K, 24.04 microampere. This is the circuit now. 470K at the base, 1 kilo ohm at the collector, beta equals 80, 12 volts. IC is, beta is given anyhow. So 24.04 microampere into 80 is 1.92 milliamperes. So when IC is given, we have to find out VCE now. VCE is 12 minus, drop across this 1 kilo ohm. 12 minus 1.92 into 1. I have purposefully removed this M and K because milli and kilo will cancel each other. So I will simply write 1.92 into 1, that is 10.08 volts. Look at this, supply voltage is 12 volts, but across the transistor it is 10.08 volts. Means transistor is nearer to cutoff region. Transistor is not fully half on. If the transistor is fully half on, here we should get 6 volts, but which is not the case. Across the transistor 10 volts is there, means only 2 volts is there across this 1 kilo ohms. This transistor is very nearer to cutoff region. Now power dissipation is VCE into IC, that is 10.08 into 1.92 milli. Voltage across the transistor is 10.08 volts. Current through the transistor is 1.92 milliampere. So it is 19.35 milliwatt. Lokesh, better luck next time. Whereas Harshita Gowda has given the answer as 19.33 milliwatt. Very good. Lokesh, somewhere some small calculation error is there. Next time, try out again. Okay, very good that students are participating. Yes, Sayan has given 19.1 milliwatt. Yes, it is correct. Let me proceed. So, this indicates that the BJT is operating nearer to cutoff region. Students, please understand this. It is nearer to cutoff region. Why? It across the transistor voltage is more than half of the VCC. If it is more than half of the VCC, it is not fully on, it is not even half on, it is slightly turned on. That is the beauty of the transistor. We can turn it slightly on, half on, fully on also by supplying sufficient current. Okay, fine. You are used to 2 digits after decimal. If you use all digits, my answer is correct. Fine. But we are electronic engineers. We always take 2 decimal places because electronics engineers, we always work with the millivolts and microvolts. We work with milliampere and microampere. Sometimes if you deal with the very small signals, then sometimes we may have to go up to 4 digits also. When you come to 5th semester, you will have one subject called CMOS VLSI design, and you will have a lab on the same circuit, same subject. And in the lab, you will be dealing with the nanoamperes also, picoamperes also. There sometimes you may have to use 4 digits as well. So always in our circuitry, in our course, throughout the semester, we will be using 2 decimal points. Next time, take care. Let me give you a small exercise. This I will discuss on my own. The measured VCE for the base bias circuit was 4.2 volts. Here in this exercise, VCE is given 4.2 volts. VCC given 10 volts. RB is given 330 kilo ohms. RC is given 3.6 kilo ohms. He is asking you to find out beta. Beta is not given. He is asking you to find out the power dissipation. So 4.2 volts is given here. Collector to emitter voltage is given, which means what? It is nearer to half on. You can see supply voltage is 10 volts. For it to be exactly half on, it has to be at 5 volts. So somewhere nearer to half on state it is there. It is neither near cutoff nor near saturation. We can say that it is at middle of the active region. In this particular example, the transistor at the middle of the active region. Now because this is 4.2 volts, because this is 10 volts, total it is 10 volts. Here it is 4.2. So naturally 10 minus 4.2 is across this 3.6K. I can easily find out IC, right? IC is 10 minus 4.2 divided by 3.6K, that is 1.61 milliampere. IB can be easily calculated, VCC minus VBE, whole thing is VCC, here it is VBE. So, VCC minus VBE divided by the resistance. So, it is 28.18 microampere. So, now beta is IC by IB, 1.61 milli divided by 28.18 micro. It is around 57. Nearest round figure is 60. That way we find out beta. Now the power dissipation is nothing but IC into VCE, voltage across the transistor into current through the transistor. Current through the transistor is 1.61 milliampere, voltage across the transistor is 4.2 volts. So here the power dissipation is 6.76 milliwatt. Can you try this out? I'll give you another 3 minutes time. Implement a base bias circuit for a quiescent point of 7.5 volts. Look at this. VCC given is 15 volts. We want it to be exactly half on. So we want VCE to be 7.5 volts and we want current to be 2 milliampere. This is our requirement. VCC is 15 volts, beta is 100. Can you find out the resistor values now? You already know the formula, right? IB is VCC minus VBE divided by RB. Now you have to find out RB. VCC you know, VBE you know. IB you can find out. IB is nothing but IC by beta. IC is 2 milliampere divided by beta is IB. So apply that in that formula and find out the value of RB. Similarly, RC you can find out. VCC minus ICRC equals VCE. VCE you already know, it is 7.5 volts. So 15 volts minus 7.5 volts divided by 2 milliampere IC will be the value of RC. Now can you quickly find out the value of RB and RC? Later on I will show you my answer. Another 3 minutes I will give you. Lokesh, this time you use decimal digits 2. Very good. Many people are giving the answer. Okay. RB is 3.75. It is not kilowatt. It must be kilo ohms. Okay. You have told it. 37.5 ohms. And it is not cyan. It is not 37.5 ohms. Such less value will not be there. Lokesh 3.75K, 715K. Okay. Let me see. 3.75K, 715K. I will show you my answer. Yes, 3.75 kilo ohms, 715 kilo ohms. Now Lokesh has got the right answer. Many students, you have got the correct answers now. Even Harshita has got the correct answer. Even Nidhi has got the correct answer. Very good. It is very simple here. We already have a 7.5 volts which we are fixing. Students, please understand, we are fixing that across the transistor we should have 7.5 volts only. It is our requirement. This is called as design. Design in the sense, We want to have 7.5 volts and 2 milliampere, exactly half on state of the transistor. We have to choose those resistor values. So RC is 15 minus 7.5 divided by 2 milli, 3.75 kilo ohms. IB is 2 milli by 100, 20 microampere. RB is 15 minus 0.7 divided by 20 microampere is 715 kilo ohms. The nearest standard value for the resistor is here 3.6 kilo ohms and RB is 750 kilo ohms. I will tell you what is meant by a standard value. For my shoes, I have a number 8, number 9 and number 10 is there, number 7 is there. For some people, number 11 also may be there, number 12 also may be there. Now, I will have to use the shoes of either 8 size or 9 size. There is no shoes of 8.5 size. I have to accommodate my feet within the size of either 8 or 9, whichever is comfortable for me. So that means that size 8 is standard, size 9 is standard, size 8.5 is not standard. Because it is not possible for the shoemakers to have shoes of all different dimensions. It will not work out for them. Because some shoes may not be sold at all. So they make standard sizes of 7, 8, 9, 10, 11 like that. Similarly, resistors when they manufacture or capacitors when they manufacture, they cannot manufacture all the values of resistors and capacitors. They make some standard values. Those standard values, the manufacturers will give it as a standard tables. I am going to show you the standard table later on. So, 3.75 kilo ohms is not available. 3.6 kilo ohms is the standard value. Similarly, 715 kilo ohms is not available. 750 kilo ohms is available as a standard value. If we don't want to use a standard value, then we have to go for some series connections. If you want 3.75 kilo only, 3.6 plus another 150 ohms in series you have to connect. Similarly, for the 715 kilo ohms, you will have to have a series connection. Whereas we can have a single standard value there. In such a case, value slightly changes. Here, 15 minus 0.7, the standard value 750K, we will get 19.07 microamperes. Collector current changes to 1.91 milliampere. VC now changes to 8.12 volts. What we wanted was 7.5 volts. Now it is 8.12 volts. There is a slight change of around 0.6 volts. It does not matter much. So the changed quiescent point is now 8.12 volt and 1.91 milliampere. This is the final value. We can standardize on these values. We will not deviate much from the accurate quiescent point. That is the point here. This is the standard resistor values table, which is called as E24 series, which is having a plus or minus 5% tolerance in its value. Which means you can see all this. 10 ohms is available, 11 ohms is available, 12 ohms, 13, 15 is available, 14 ohms is not available. 16, 18, 20, 22, 24, 27, 30, 23 is not available. See? Again 25, 26 are not available, 30 is available. Similarly 33, 36, 39, 43, 47, 51, 56, 62, 68, 75, 82, 91. This is called E24 series, which has got totally, you can see, 24 values are there, though it is called as a E24 series. So in this series, now you can see 75 is there, 71.5 is not there. That is why 750 kilo ohms is standard. 75 is standard, 750 is standard, 7500 is standard. Okay. Similarly, one more value was 3.6K. You can see 36 is standard, 33 is standard. Now, our calculation of 3.75, that is not standard. So, this is called E24 series. You don't have to remember this number.